Just over a week ago, AMD finalized its acquisition of Xilinx, a company that specializes in FPGAs, in an astounding all-stock deal of $35 billion. Today we will look at what an FPGA is, what this acquisition means for AMD, and what this acquisition means for PC enthusiasts in particular. This video is sponsored by UCDkeys.com. UCD Keys offers Windows 10 and Windows 11 Pro keys at super affordable prices. Currently, they have Windows 11 Pro for $21 and Windows 10, which is what I personally use, for just $14. There's also Office keys of various kinds. I've used this service myself, as have lots of my patrons and viewers, and the service works great, and the keys work globally. We're partnering with UCD Keys for a special offer. By using the coupon code C30, you will get an additional 20% off of any purchase. Visit ucdkeys.com or click the links in the description. The first thing we should address is what exactly an FPGA is. So a CPU consists of non-configurable logic blocks, and so does a GPU. They cannot be configured to do anything other than what they were designed to do. They can be programmed via software, but on the hardware level, their capabilities are fixed. An FPGA, on the other hand, can be configured to do different types of computation, even after the chip has been taped out and has been released. A CPU is great for serial processing. A GPU is great for fast parallel processing. An ASIC, like a Bitcoin miner, is great for accelerating specific computations. An FPGA differs from all of these because it can be configured to support hard-coded algorithms for specific applications, whereas an ASIC is custom designed for large-scale specific tasks. Let's try and simplify this with a concrete example like Bitcoin mining. A Bitcoin mining ASIC is a device designed specifically to run a mining algorithm. The algorithm already exists. It's a known quantity, so a piece of silicon can be designed to run this algorithm optimally and nothing else. It will perform better than a CPU at mining because a CPU is a general-purpose device with lots of different blocks for different operations. A CPU can mine, yes, but only using a small portion of its various components, making it much slower than an ASIC. An ASIC will also typically be better than a GPU at mining, because even though a GPU is parallel in nature, it has been designed with shaders in mind for rendering pixels and not specifically for mining workloads. A GPU can mine, but it won't use all of its resources to do so, while a Bitcoin ASIC will be fully used for mining. That's what it's been custom designed to do. While an FPGA isn't designed with a specific workload like mining in mind, it can be configured to do mining, but it won't typically outperform an ASIC that's been custom designed for mining, so it doesn't make much sense to use an FPGA for mining. So what is an FPGA good for? Well, let's say that instead of mining Bitcoin, which relies on established algorithms that rarely change, we use artificial intelligence as an example. In AI, algorithms are constantly evolving, so if you custom design an ASIC to run an AI algorithm, like you would with mining, while it would work for that algorithm initially, as soon as that algorithm was improved upon by the developer community, you'd have to throw those ASICs away and build new ones designed for the new algorithm. Considering AI algorithms change every few months, it would be crazy to be designing and deploying ASICs every 2 months to run these. It just wouldn't make sense financially. So typically, AI algorithms are adapted to run on something like a GPU, but GPUs have limitations, and algorithms have to be restricted to what GPUs are capable of doing. This is where an FPGA can be a great solution. An FPGA can be configured to run an existing algorithm and then reprogrammed to run a new algorithm when the developer community optimizes it, and then a new one, and so on, because its blocks are configurable even after it has been manufactured. This gives developers a lot more room to create complex algorithms that can take advantage of specific FPGA blocks, meaning an FPGA is incredibly flexible. It can be deployed and altered over time without the need for new hardware. So does that mean everything should just run on FPGAs, seeing as they're so flexible? No, the optimal approach for a hybrid processing system is to have a good balance of CPU, GPU, FPGA, and ASIC accelerators. All of these have their optimal uses, and this is where AMD's acquisition comes into play in balanced heterogeneous systems. We will look at specific examples in a minute. Traditionally, FPGAs were seen as great prototyping tools and nothing more, but as they have become more powerful and as new IP blocks like DSPs have been added, FPGAs have gained a life beyond prototyping, with applications in accelerating automotive, industrial, data center, medical, broadcast, video and image processing, wired and wireless communications, aerospace, and a lot more areas. And guess who is the leader in the FPGA market? Xilinx, the company that is now a part of AMD. By acquiring Xilinx, AMD gains an additional total addressable market that can greatly boost its revenue and profits over time in areas where AMD wasn't directly involved. But surely if AMD spent a whopping $35 billion in acquiring Xilinx, there must also be a direct benefit to AMD's current products, right? Well, yes indeed, and the possibilities here are really exciting. While there haven't been any official announcements on specific products, AMD have already stated that the first AMD product with Xilinx IP will be out before the end of 2023. If I were to guess, the first applications of Xilinx IP in AMD products will be aimed at the cloud. While I use the AI or machine learning example above, the reality is that machine learning is not at a scale yet where FPGAs could be viable, although we are rapidly getting there, and FPGAs have proven very effective at inference workloads. But in the cloud, things are different. For instance, Google Search would greatly benefit from hardware that could be rapidly reconfigured to keep up with software. An FPGA could be used here for accelerating SQL queries, for instance. Or let's say Google's developers add a feature to Google Search where you can search for things in videos. Imagine that you are watching a video and something in the background catches your eye. You pause the video and click on the object, and a Google search pops up and tells you what this object is and how you can buy it. With FPGAs, Google's software and hardware engineers could reconfigure the FPGAs to run these types of searches. And because of the nature of FPGAs, this could be done in weeks. Google wouldn't have to wait 2 years for a specialized ASIC to be developed to accelerate this novel search. If this type of search didn't catch on with users, the FPGAs could be reconfigured to accelerate something else. This is the power of FPGAs in the cloud. This is just an example, but loads of different use cases apply here, particularly in networking itself. So in this example of a video search based on image recognition, AMD could create a chip composed of several ASIC CPU chiplets, an Instinct GPU chiplet, an FPGA chip, and gigabytes of shared memory on top of the package, all linked with Infinity Fabric. This would give AMD an incredibly appealing fully integrated product for cloud that it could sell in volume with high margins. Note that each FPGA would be part of a pool, which means hosts running services that do not use their local FPGAs could donate them to a global pool. In other words, some FPGAs could be running SQL acceleration, while others could be configured to run image recognition, and so on. This is a whole new paradigm for the cloud with incredible flexibility and speed of deployment. At the moment, to create a system like this, you need a bunch of discrete devices, all connected through PCIe, which is not ideal as there's a lot of latency involved there. If we go by AMD's recent history, which has been mostly cautious of creating niche products without a customer already lined up for it, it's possible that AMD already has a partner interested in a hybrid ASIC/Xilinx chip. Of course, AMD could just take the build it and they will come approach and add an FPGA to the ASIC package and hope it can sell it to hyperscalers. But knowing Lisa Su's CPU's cautious and pragmatic nature, I think it's more likely that the product they will announce next year that features Xilinx IP will be something custom-made in partnership with a hyperscaler, something that they can then adapt for other customers. At least that's my guess. Of course, beyond this, one can dream of what AMD could do with FPGAs beyond just cloud and enterprise. AMD could create a Zen 4, or more realistically a Zen 5 core, with more cores on the die or larger cores, with the expectation that an FPGA could take the load off the CPU. Larger cores would be ideal, as the CPU would almost exclusively be focusing on serial performance. Next to the core die would be a Xilinx FPGA with no ARM IP, seeing as we already have Zen for general purpose. An RDNA 3 die on the SoC would be dedicated to graphics, and on top of all this would be 3D cache, of course. Tons of Infinity fabric lanes would connect it all. In other words, a heterogeneous client chip. Are we at the point where we need this sort of chip on the desktop? I think we are on the verge of needing heterogeneous systems on the PC for two reasons. Firstly, cost. It's getting too expensive to be on the latest nodes, and AMD is at the mercy of TSMC's hunger for higher margins. I think it might become impossible to continue building monster CPUs on TSMC's newer nodes, even with a chiplet strategy, unless AMD is fine with passing those costs down to consumers, a strategy that I think is too risky. So the alternative is to offload as much as possible off of the CPU cores and into accelerators. Beyond costs, another reason for a heterogeneous strategy on the PC is new AI-based workloads, as well as intense compute workloads in things like gaming, as we've seen with real-time ray tracing recently. Imagine this scenario: ray tracing becoming more prevalent, accelerators for it don't have to be a part of the GPU. They could go on the CPU SoC. AMD could add an FPGA accelerator that can be configured to do ray tracing, and then tell gamers that if they pair their GPUs with an AMD Zen CPU, they will get much faster ray tracing performance. This would require some impressive software and hardware co-design, but it's doable. It could even work better if you combine an AMD GPU with an AMD CPU. It's a value proposition on the CPU side that goes beyond just more cores or higher frequency. And beyond gaming, this FPGA portion could be configured for specific needs. You could have a configuration for video editing and rendering, or a configuration that's specifically tailored for Photoshop or for AI workloads like speech recognition or image recognition. AMD could have a bunch of different configurations in a special tool similar to Radeon software, where you would be able to choose a profile for each of these specializations as needed. And as software developers worked with AMD to implement new functionality, it could be added to this app. I mean, the possibilities here are truly exciting. Let's say Intel launches a new CPU that's beating Ryzen in Cinebench multi-thread. AMD can release a configuration for the FPGA portion of their existing products with FPGAs on them that targets that type of tile-based rendering and get the performance crown back. Think of what Intel is currently doing with Adobe. They have ASIC blocks on their chips that accelerate specific software functions in Photoshop and Premiere. So rendering video when using Intel's HEVC acceleration, for instance, is faster than regular CPU plus GPU rendering on other platforms. But those blocks on Intel's chips are fixed. They can't do any other types of workloads other than what they've been designed to accelerate. With an FPGA, on the other hand, the hardware could be tailored to your needs. So if you're not a Photoshop or Premiere user, the FPGA block can still be used for something else, including gaming-related workloads. Of course, this all requires software and hardware co-design, something that AMD hasn't been particularly good at on the client side, unless backed up financially by someone else like they've done with the consoles or with Apple. But with the Xilinx acquisition, AMD got not just the IP, but also Xilinx developers, and my guess is that that's where a software/hardware co-design division will emerge. Another avenue for software/hardware optimization is opening up the FPGA blocks for developers. Xilinx has their ACAP platform with an emphasis on attracting developers away from CPU and GPU programming and into their FPGA environment. Developers are able to code with C and C++, OpenCL, and Python and create libraries that target particular applications and domains. This is of course aimed at the cloud and enterprise, but if If AMD brings this to their PC products like Ryzen, this could create a revolution of application-specific coding for all sorts of niches, including gaming. As in the example I mentioned, an intrepid developer could create an acceleration program for ray tracing in games that makes use of the FPGA blocks in a future Ryzen product to massively improve performance in real-time ray tracing in games. One could argue that the value proposition for bringing FPGAs to the PC isn't there, and it would only add cost to the CPU while going mostly unused if the developer community doesn't take to it. But the same could have been said about going mainstream with 16-core CPUs on the desktop. Just a few years ago, it would have seemed pointless, yet AMD managed to market the extra cores as a feature and ended up taking up a dominant position in the CPU market precisely thanks to that novelty. So I definitely wouldn't discount FPGAs on the desktop. With the right marketing, it could become a major selling point. Now, the biggest winner of this AMD acquisition is Xilinx themselves. Xilinx has remained the leader in the segment, but it has offered exclusively discrete monolithic cards. As you know, communication between a CPU and a discrete card over PCIe creates a lot of latency. With Altera, Intel aimed to significantly reduce latency by having the FPGA on package, something that Xilinx couldn't compete against. But now, with AMD, Xilinx FPGAs will exist both as discrete options and in package, presumably first with EPYC and hopefully at some point with Ryzen. So one could argue that in this acquisition, Xilinx has a lot more to win than AMD, but like I said, AMD wouldn't have spent $35 billion to acquire Xilinx just to increase TAM. For reference, that's almost twice what Intel paid for Altera. The point of FPGAs is to offload workloads off of the precious CPU cores, especially in an age where data analytics and database processing are prevalent. Having the CPU waste resources on housekeeping type of workloads is a trend that is going away. So AMD has the CPU advantage over Intel, currently in the number of cores and later this year probably in serial speed, and it has the price advantage over Intel. Offering an FPGA means it can strengthen the speed advantage even further, because less CPU resources will need to be allocated to tasks that can now be taken up by the FPGA blocks. What this means is that as CPU core and frequency scaling levels off with the end of Moore's law, AMD can guarantee that it stays ahead of Intel performance-wise by making more of the CPU available to computation, with other workloads offloaded to accelerators like FPGAs. It's a perfect marriage, and both AMD and Xilinx are a lot stronger together than they were apart. Now, of course, AMD's rival, Intel, has been in the FPGA game for several years now, although without significant success revenue-wise. Intel has launched a hybrid CPU/FPGA system using the ARIA FPGA IP that it acquired from Altera in combination with its Xeon Skylake SP chips, but these haven't really materialized in scale. Intel has had reasonable success with discrete FPGAs combined with Xeons, particularly with Microsoft's Azure cloud. But as far as a hybrid chip is concerned, Intel has failed so far to deliver something solid. It seems the strategy on Intel's side is to leverage better connectivity between CPU and discrete accelerators going forward, using for instance CXL, instead of integrating an FPGA into a Xeon package. Basically, the thinking here is the same for GPUs in the data center. They seem to be doing just fine running over PCIe rather than being integrated. Several years after the Altera acquisition, Intel hasn't yet delivered a solid heterogeneous product that combines Xeon and FPGAs. It seems AMD might be the ones pulling that off on a significant scale. So to conclude, offloading network and storage off of the CPU and to data processing units helps cut latency, helps improve throughput, and lowers cost. And both AMD and Intel are moving towards this in the data center. But there's a broader vision here that needs to be considered. How are people going to use computers and personal devices in the next decade? Is local processing, so that means processing happening on your PC, going to greatly benefit from a variety of accelerators? I think the collaboration between Adobe and Intel has shown that there is a significant benefit to users in having dedicated hardware for specific tasks, from encoding to artificial intelligence, and AMD will need to evaluate carefully if a heterogeneous strategy makes sense on the PC. It could be the case that bringing FPGAs to the PC would be a stroke of genius and start an acceleration revolution, or it could be a complete disaster, making Ryzen CPUs more bloated and expensive for no reason, with the FPGA portion left unused. If you saw my last video, you know that Intel has a chiplets-based strategy that will encompass all of their products, so having these accelerators on the PC is only a matter of time in my opinion. If AMD doesn't want to be caught off guard, perhaps taking the lead in bringing FPGAs to client devices is not so crazy. Build it and they will come. And this video was made possible by my awesome patrons. YouTube revenue is now almost non-existent, so it's up to you guys to support smaller channels like mine. Join my Patreon today and get exclusive access to the Cortex Discord server, where a welcoming community of enthusiasts discusses technology daily and where I often share exclusive bits of information. If you can't contribute financially at this point, then please give this video a like and share it with friends, as that really helps. Thanks for watching, and until the next one.